So hello, good morning, California, good afternoon, good evening, everybody, wherever it might be. It is my great pleasure to welcome THERESE LANDRY as our today's speaker, and she will tell us about spectral triples, non-commutative solenoids, and things like this. THERESE, the floor is yours. Take it away.
Hey, thank you very much. And of course, thank you to the organizers for this opportunity to present this work done in collaboration with Nadia Larson, Carla Farsi, and Judith Packer. So what's a motivation for studying non-commutative solenoids? Well, non-commutative solenoids are very rich in structure. First off, they can be viewed as twisted discrete abelian group C-star algebras. And as C-star algebras, these non-commutative solenoids are star isomorphic to inductive limits of non-commutative tori. And moreover, the underlying groups are not finitely generated. So to study non-commutative solenoids, we use tools from non-commutative geometry, and they will, using these tools from non-commutative geometry, non-commutative solenoids can be viewed as quantum analogs of manifolds via spectral triples in the sense of Kahn. And they can also be given a quantum analog of compact metric space structure in the sense of Riefel. And the constructions of both of these non-commutative structures will rely on that of length functions from groups. So both constructions will make use of length functions on groups, and additional properties for the length functions on the groups will lead to additional properties in these quantum structures. So what is a twisted group C-star algebra? So that's one of our first layers of structure that we'll examine for the non-commutative solenoid. So if you have a discrete group, then the twist comes from the multiplier, a multiplier on the group. So that's a 2 cocycle on the group taking values in the unit circle. And the multiplier gives a twist it plays the role of the twist in the definition of the twisted convolution product, and also in the adjoint operation. And for the left regular representation of the twisted L1 functions on the L2 functions on the group is defined for all the L1 functions and all the twisted L1 functions in this way. And in the case when the group is amenable, like it is in our setting, then the full twisted group C-star algebra associated to this multiplier coincides exactly with the C-star completion of the twisted L1 functions in the norm given by this representation. So I said that the underlying groups for the twisted group C-star algebra structure of non-commutative solenoids are not finitely generated. So here's an example of a finitely generated twisted discrete group C-star algebra. And as we'll see, the class of twisted group C-star algebras includes some very well understood examples in non-commutative geometry. So a twisted group C-star algebra can also be viewed as a universal C-star algebra. So namely the one generated by a family of unitaries indexed by the elements in the group. And then the twist plays the role of, the twist or the multiplier, it plays the role in defining the commutation relations between any two of these unitaries. So then if we take, say, the discrete group Z2, which has only 2 elements, we could define a multiplier in this way. And this is one way to define the non-commutative theta torus as a twisted group C-star algebra. So again, you can see that because Z2 has only 2 elements, then the underlying group is finitely generated. And of course, this is star isomorphic to the rotation algebra, which is the universal C-star algebra generated by 2 unitaries, again, subject to this commutation relation.
Sorry, I have a question.
Mhm.
What is this subscript n at theta in the exponential?
N. Oh, that should not be there. That's a typo. Thank
Okay.
you. Okay, so to see that non-commutative solenoids, that the underlying groups are not finitely generated, well, one of the building blocks is ZP, which you can see is not finitely generated. So what is ZP? That's for a fixed prime P. Let the group of p-adic, that's a group of p-adic integers endowed with the discrete topology. And so this underlying group is not finitely generated. And so to define a multiplier on this group, we have countable sequences of values from 0 in the unit interval and subject. So if I have a fixed P, then each of the adjacent elements in this sequence are subject to this congruence relation. And so then given a choice of such sequence in omega p, then we could define a multiplier on ZP cross ZP. So that'll be our discrete group. And so taking 2 elements in ZP, here is an example of a multiplier on this discrete.
Sorry, these thetas are where? These are irrational numbers. What are these thetas?
They can be rational or irrational.
Irrational, yes. Okay.
So they can be anything from 0 up to strictly less than 1.
Okay, but then it just picks theta 1 and the rest follows, right? Because just powers of P.
No, it's a convergence modulo.
Ah, it's modulo Z.
Yes, it's modulo.
Okay.
So there's a restriction on the adjacent elements in the sequence. So then the non-commutative theta solenoid is given by this twisted group C-star algebra. So with a multiplier defined in this sort of way, and then with the underlying discrete group being ZP cross ZP, which again, I'll point out is not finitely generated.
I have a question. Provided all thetas are rational, do we obtain in this way the classical solenoid C-star algebra?
Well, I guess is the classical solenoid. So what kind of rotation algebras are in the classical solenoid? Are they all commutative tori in the classical solenoid? Hello?
Yes.
So in the how is the classical
What's the
solenoid?
question?
So you asked about the classical solenoid.
Yeah.
So with the classical solenoid, can that be written as an inductive limit of
Yes.
commutative tori?
Yes. More and more so-called satellites.
Right, but then
Yes.
all right, but then as we'll see actually in the next slide though, then because each of these sequences, you associate the corresponding rotation algebra. and this is not commutative.
Yes.
I mean, this is, yeah, this is not commutative.
Mhm.
So I would say that, so does a commutative solenoid have to be an inductive, can it only be realized as an inductive limit of commutative tori?
Yes, probably, yes.
Right, so then that would
algebras
limit
are not
then what you
commutative.
could have in this realization as inductive limit of C-star algebras, which would then determine what kinds of sequences you could have here. Which maybe I'll say then should be maybe 0 through. I have to think about that. Okay, so, but that's something I should think about, the commutative solenoids. So how can one view non-commutative solenoids as inductive limits of non-commutative tori? So that is, so this is something that La Tremoliere and Packer accomplished. And so to do that, fix a prime P and pick one of these sequences in omega P. And so for each of the entries in the sequence, associate the corresponding rotation algebra. So again, using like the rotation algebra that is star isomorphic to the quantum torus with subject to that sort of commutation relation where theta is encoded. And so looking at the even entries in the sequence and the associated rotation algebras. So it turns out that if you take so taking as your star morphisms, the unique ones extending these unitaries to this one, and taking these as your connecting maps, then the non-commutative theosolenoid is star isomorphic to this to the inductive limit of this particular sequence of quantum or of rotation algebras. So in this project, non-commutative solenoids, they'll be they can be viewed as quantum manifolds via spectral triples in the sense of Kohn. So a spectral triple, the triple consists of a unital C-star algebra and a unital faithful representation of the C-star algebra on a Hilbert space, and a distinguished operator on that Hilbert space that exhibits the following properties. So the first one is that this operator have compact resolvent. And what that does is allows for the extraction of like notions of metric and measure from spectral data. And the next one is that there exists a dense star subalgebra of the C-star algebra such that the commutators with the distinguished operator is densely defined and extends to a bounded operator on the Hilbert space. So in analogy with like the manifold setting, this is analogous to the denseness of the smooth functions in C of M for M manifold. And when this operator exhibits all those properties, then it's called a Dirac operator. And especially in our setting, we're going to highlight the role of the subalgebra and it's sometimes referred to as a smooth subalgebra with respect to this operator. And so that's going, as you can see, this is going to be something that we're going to develop later on in the talk today.
So you don't assume this order one condition.
The what?
One condition, nor reality, nothing.
This is a naked
Naked spectral triple. Okay.
I haven't worked with more complicated spectral triples yet. This is, yes.
Only to
Okay.
X. Okay.
But I hopefully maybe in my career at some point, I will have the chance to develop.
But sorry, the order one condition is the condition that the commutator are bounded, yes? So I think the order one condition is there.
Where?
Yeah, I don't know what that.
Now, order one is about commutators with commutators.
It's a commutator with this commutator with D, but of the representation which is star. Okay, star.
Okay,
of
so
pi.
this one,
For order one, you need J, the real structure, is not
yeah.
for this.
Okay, I see. Okay, thank you.
So in the context of smooth subalgebras, this is usual condition.
So this is a usual condition when studying the smooth subalgebra. Okay, and so spectral triples, non-commutative geometry via spectral triples can be viewed as a quantum analog of Riemannian geometry, because in the Riemannian setting, the geodesic distance encodes the geometry of the manifold, and in the prototypical setting of a spin manifold, Kahn showed that the geodesic distance can be recovered through purely operator algebraic data, namely the C-star algebra C of X, the Hilbert space being the L2 spinners, and then the Dirac operator in that particular setting. And so, of course,
Sorry. In your definition of L, you are integrating something to the square root of the metric tensor. Are you suggesting here something, or?
so here I'm suggesting that this
Not the
is
usual
meant to
formula.
represent the classical sort of, or the classical Riemannian way of defining a length. So the existence of sufficiently well-behaved paths in the space.
So I'm asking because the square root of this tensor sometimes is meant in terms of the Clifford algebra, but written in this form, it's some non-standard writing of the usual formula for the length of the curve.
Yeah.
I suppose.
Also, I have a problem with gamma being on the left-hand side and not being on the right-hand side. Something is wrong in this formula.
With gamma here?
Yeah, where is gamma here?
So gamma is deformed into this integration sign.
Wait, but gamma is the path.
Yes.
Yeah.
Ah, okay. So that's what you mean. But okay. Sorry. Yeah. That's.
Yeah, you integrated one form over a path, but it would be better. I mean, you just integrated the velocity vector. Is mathematical notation is better,
Yes.
right?
Yes, Francesca. I think so. Yes.
So you would suggest putting the vector instead of
The Riemannian norm of the velocity vector, gamma prime of t.
Yeah.
You take the norm, where the norm you compute with the metric and just integrate in the t, in the range of t.
Yes, so exactly. So when t ranges, I don't know, from 0 to 1, and you have a path which at gamma 0 is p, at gamma 1 is q, and when gamma should be under the integral side, yeah, and we integrate over the unit integral, yes.
Well, I guess here what I wanted to try to emphasize was that in the more general setting that the quantum space doesn't need to be able to admit a path. In a sense.
So this way of writing anticipates this introduction of tenor in a sense, because you can understand this formula in two ways. Okay, it's either an integration along the path, or you are introducing something related to the square root of this tensor of this metric tensor, which needs this gamma matrices. Okay, It's different algebra, otherwise. That makes sense, okay.
Right.
It's not
Maybe I-
evaluated out of the target vector.
Maybe I need to rethink how because I wanted to emphasize the pathless versus the operator algebraic, purely operator algebraic data.
Yeah, but as long as you write something in terms of differential geometry, it should make rigorous sense in differential geometry. Yeah, but I guess what Francesco said is clarified.
Yeah, I mean, in any case, that is a standard formula in differential geometry books that are oriented to physicists. Maybe for a mathematician, the other formula is better, but you can find this in books. You just have to interpret the square root. It's not an actual square root of a two form. I mean, it has
Yeah.
And so the spectral triple is constructed using link functions on. Is that being covered by the screen sharing? So link functions on discrete groups. And so these were studied by Kahn and also Christ and Riefel, and studied in the twisted setting by Long and Wu. So what is a length function? Well, it's defined on a discrete group, and it is a non-negative valued function that vanishes on the identity.
Sorry, Theresa, could you somehow move this bar you are screen sharing because it obstructs the title of the slide?
Yeah, that's what I was wondering about. Maybe that's
This is strange. It's the first time I encountered it, to be honest.
I'm surprised that it shows up.
Should hide.
It should hide.
Moment, automatically.
Right. Well, when I logged in this morning, then the Zoom automatically made updates. So maybe this new version.
I doubt it, but
Maybe that's, or maybe,
because I know that when we are doing screen sharing, having a speaker on site, then I can move.
Oh, this is better.
Yeah, this is better.
Yeah, somehow
This is
it
better,
went-
yes.
I don't know how it did that, but I'm glad that it did.
Yeah.
Okay, so this is a non-negative valued function that vanishes on the identity. It takes the same value, its value on an element, and its inverse is the same. And we also have a kind of sub-additive property. And some additional properties that a link function on a discrete group may have, and that, as we'll see, lead to additional quantum structures, is it's said to be proper if balls with respect to those link functions are finite sets. And a proper link function can also be said to be a bounded doubling if there exists a constant, so a way to control the size or growth of balls with respect to the length function. So how does one build spectral triples from length functions on groups? Well, if you have a length function on a discrete group, then take as an operator this usually unbounded operator on the L2 functions of pointwise multiplication by the length function, a multiplier on the discrete group, and the left regular projective representation of the group on the L2 functions. And here's one of the key equalities building on the work of Christ and Riefel. Long and Wu showed that given any element of the group, if you take the commutator, the norm of the commutator with this operator and the Dirac function, then that gives you exactly the length of the group element. And in particular, when your function is a continuous function of compact support, a twist, then this extends to a bounded operator on the L2 functions.
Sorry, Theresa, may I ask you an indiscreet question? Because this paper of Long and Wu, which you sent me, This is not on the archive. How did you come across this?
So that was Carla Farsi found that article.
because it's published in some Chinese journal. Yes, in English, I admit it, but it's not on archive. And I mean, I was amazed that I couldn't find these guys at all. They don't exist on archive. I mean, they have no
Great,
papers
so-
on archive.
Yeah, so that was entirely Carla Farsi found that paper.
Yeah, she's good at it. She also pointed me some great references. Yes. Okay. Okay.
I mean, surprisingly, I think like they don't seem to refer to too much in quantum compact metric spaces, you know, people working after refill. So there isn't like their terminology is, you know, in a way like very
Yeah, I mean, they look isolated, right? I mean, like in pre-internet era where people would just sit at home and write on a piece of paper.
I think they were at East China, or they're at East China Normal University, so there's a very active operator algebras.
Anyway, so it was Carla. Okay.
Yes. So and so in particular, this
Sorry, probably in this last but one line in black, this vertical norm sign is not necessary.
Oh,
Yes.
you're right.
Yes.
That's true.
So
Yes.
second typo, 2-0 for us.
Thank you. I'll have to take note of that. So then when you have a dense, so because the continuous functions of compact support are dense, then any length function in this setting can be used to build a Candice-Dirac operator for a spectral triple that satisfies the second condition, the denseness condition. So that's without requiring additional properties on the length function yet. So we'll see what adding the proper condition, what adding the bounded doubling condition gets you in terms of additional structures.
Sorry, just a quick question. Your group is countable discrete, yes? So I think that it isn't necessary to write continuous functions with compact support. It is just finitely supported functions and all possible functions. Every function is continuous automatically. Your gamma is discrete, yes. So
Yes.
Yes, I think that's true. I think maybe just for the ease of communication in the proofs for the reader.
so this algebra is something like a polynomial ring, yes. So maybe this also corresponds to the fact that we do not want to assume all the other conditions of spectral triples, since your algebra is not something like a smooth function, but something rather like polynomials, yes.
Yes.
So just a quick remark. Sorry.
Oh no, that's good for my mathematical culture. So we can also construct finitely spectral triples from length functions with bounded doubling. So a spectral triple is said to be finitely summable if there exists a positive constant S such that the identity plus the Dirac operator squared to the power of negative S over 2 is a trace class operator. And when we have a finitely generated discrete group with a length function that has polynomial growth, Kahn showed that the associated spectral triple is finitely summable. And Christ and Riefel demonstrated that length functions on discrete groups that are bounded doubling also exhibit polynomial growth. And well, in contrast to the setting considered by Kahn, note that our underlying groups are not finitely generated.
Sorry, just a silly question. If you look at this finitely summable spectral triple, is it true that when I take sort of a signature of a Dirac operator and go from a spectral triple to its Fredholm module, then finite summability of a spectral triple will imply the finite summability of a Fredholm module? It should be like this, right? But
As
I'm just
far as I remember, the answer is positive for one of this question, which one can ask, since you can also construct the Dirac operators in terms of Fredholm operator, like a sign of a Dirac. And one implication is the other is not, and I don't remember which one is true, but probably this one which you have mentioned.
okay, yeah,
So
because
that I'm not familiar with, being very new to finitely summable spectral triples.
But as far as I remember, the second direction of the implication is false. So
yeah, but I suppose you're right, because you have sort of the Fredholm module behind the spectral triple, but there is a non-obvious lift of a Fredholm module through a spectral triple. And probably you could have some weird lifts that would screw out the summability. This I can imagine.
yeah.
Yeah.
Sounds
Although
probable.
I definitely cannot even fathom a counterexample at this point.
So in these two notions, different operators play a role. Here you have this Dirac operator, and in this Fredholm module, it is a sign
Yes.
of this operator. So it's quite natural.
The question is that you need an extra condition which people call Lipschitz condition. If you have Lipschitz condition, then you get from the spectral triple finite summable a finite summable Fredholm module.
But
So the module of the Dirac operator has to have bound the commutators. Then from a summable spectral triple, you get a summable Fredholm module.
okay, thank you, Elmar. Yes, good. Thank you.
Provided this operator F from the Fredholm module comes as
Yeah.
sign. Right?
Yes, again, yeah.
Of course.
Okay, I find it interesting. Okay, thanks.
And I learned a lot of things.
I'm happy.
Okay, so, well, of course, then, do such length functions exist, like do length functions of bounded doubling exist on ZP cross ZP? And to construct one, so let's first define a length function on ZP. So this is defined as the sum of the usual absolute value plus the p-adic norm, where the p-adic norm is very small. The higher the powers of p divide the number. And so then taking this length function, then the actual length function that we use is take the sum of each of those on the components of ZP cross ZP. And you can show that that's actually a length function on ZP cross ZP. And not only is it a length function, it's a length function of bounded doubling. And here's the particular constant that controls that, which you can like control the growth of balls. So then using this particular length function, then we were able to construct a spectral triple, so fix a prime P. And so we have ZP cross ZP. Our Hilbert space are the L2 functions. And so pick a sequence in omega P. And as the representation, take the left sigma regular representation. And for the Dirac operator, take the multiplication by the pointwise multiplication by the length function. And so then this choice, so the non-commutative solenoid with this choice of Hilbert space and this choice of Dirac operator and this representation is a spectral triple with associated smooth subalgebra, the continuous functions of compact support on the twisted group. And furthermore, this is also, the spectral triple happens to also be finitely summable. And the finite summability condition is actually a consequence of the bounded doubling condition for the length function. On the other hand, to verify the compact resolving condition, then that's something that relies on the length function being proper. So you can see that in the proof. So if you, so to verify that, so take the, so note that the Dirac functions are eigenvectors of this Dirac operator with the eigenvalues being the length of the corresponding element of the group. So then this means that the eigenvectors of the Dirac operator minus 1 over the Dirac operator minus IT times the identity has this particular eigenvalue. And so to show that this is compact for some fixed non-zero value of t, choose some epsilon greater than 0. Then there exists some positive real number r, so that any number bigger than this r implies that z minus 1 over z minus it is less than epsilon. And given such an r, and our length function then defined a ball with respect to this length function and this value of r. And so this is where the rule of being proper comes in. So since the length function is proper, this is going to be a finite set. So this is going to allow us to build our finite rank operators. So to build our finite rank operators, let's take an enumeration of elements in this finite set and take the orthogonal projection from taking the L2 functions onto the one-dimensional subspace spanned by each Dirac function. And so here's our finite rank operator. And because of the conditions that we put, then the difference, so this is different in norm. The difference in norm is bounded by epsilon. And so therefore, this is a proximal norm by finite rank operators. And so therefore we verified the compact resolvent condition.
Sorry, I have a question. I have a question for the motivation for this function L. Because if you have this Archimedean norm, okay, and this p-adic norm, then you know that when one is big, the second one is small. Okay. So what is the intuition of or motivation for taking this combination of this Archimedean norm and this p-adic norm?
So there wasn't really an intuition. It was just, it seemed to, so Judith Packer tried it and it worked. And then I worked out the bounded doubling.
It satisfies this doubling and the finiteness, this properness and doubling.
Yes.
Okay, it's easy to prove for this. Okay, and
yes, so it's actually, if you look in the paper, the proof is, it's pretty elementary. So it doesn't getting the bounded doubling constant. But I always did find that
this
kind
is
of
one possible choice of many possible. So
the possible choice of what?
It's only one choice of many possible choices
Of L.
of L.
There probably are other choices of L, but this was one that we showed works.
Is it true that many choices are equivalent in a sense at the end of the day?
I haven't thought about that, but that.
Sorry, what does it mean equivalent in the context of spectral triples?
Provided that both satisfy this properness and doubling property, so maybe there is some equivalence between these spectral triples, because
yes, but how do you understand equivalence between spectral triples?
I don't know. I don't know, but But if this is about some non-commutative solenoid, so I expect that there is some object which we described in some way.
Hmm.
You
If
mean for
this is
different choices
if this is
of
only
length
a description, if this is only a description void of something existing independently of this description, that I'm starting thinking, what is this story about? Okay. Why this choice? If we take, okay, if you take another L function,
Mhm.
would you call this limiting object also a kind of non-commutative solenoid?
Well, but the non-commutative solenoid doesn't rely on a length function to define it. So it's just flipping the
They would be
non-commutative
equivalent in some
solenoid.
sense.
Wait, the length function with these additional properties allows you to equip the non-commutative solenoid with a spectral triple.
Mhm.
If it has an additional property, it allows you that spectral triple to have additional properties like finite summability. And then with yet some more properties, we could get ones that induce quantum compact metric spaces.
Okay, so it's a kind of fixing kind of metric structure on this solenoid, in a sense.
Right, so it adds a kind of, yes, quantum sort of structure, quantum metric structure.
But topologically, it's only one solenoid.
Yeah.
Okay.
As a sister algebra.
Yeah.
The sister algebra doesn't depend on
Directly,
the of
yes.
that. Yeah. Mhm. It's an additional.
Right.
So we are speaking about some class of a non-commutative metric structure on a solenoid, on a non-commutative solenoid. Yes.
Yeah.
Okay, so I get it now. Yeah.
Good.
Okay, and it turns out that also our spectral triples, that we could define restrictions for each of the different components so that we get spectral triples on quantum tori. And of course, that's interesting because non-commutative solenoids can be realized as inductive limits of quantum tori. So if you take the restriction of, say, LP to 1 over P to the NZ and define it again similarly with each of the components. And so take this as the restriction of our length function, and you restrict the multiplier accordingly. Then there exists a star isomorphism that takes this twisted group C star algebra so between Z2 equipped with this multiplier to this particular twisted group C star algebra. You can use also that star isomorphism to define a Dirac operator, and then also adjusting the representation accordingly. Then you get a spectral triple for the non-commutative torus with associated smooth subalgebra being the continuous functions of compact support on this twisted group C star algebra. So so our spectral triples also reduce to spectral triples on each of the respective non-commutative tori, out of which the inductive limit is made. So then, well, actually a motivating question at the beginning of when we first met about this project was, well, since non-commutative solenoids can be realized as direct limits of non-commutative tori, well, are there spectral triples on non-commutative solenoids that can be produced as limits of spectral triples on non-commutative tori? So where both the limit structure, the direct limit structure at the level of the solenoid is also mirrored in a sort of inductive limit structure in the spectral triple. And so that led us to the work of Florcel and Gorbanpour. And so to define an inductive system of spectral triples, we have a directed index set. And accordingly, we have a family of spectral triples with each with their respective smooth subalgebras. And so this highlighting the smooth subalgebras, that's something that wasn't really in Florcel and Gorbanpour's work, but we added to their framework. So that was something we chose to add so that we could also lay the groundwork for studying these smooth subalgebras later.
So sorry, but these are subalgebras of what?
So these are subalgebras for each of these unital, like each of the unital C-star algebras in the spectral triple.
So this is
So we have a
script.
family of spectral
Oh, I'm
triples.
sorry. Yes. Oh, I'm so sorry. Yes, of course. Thank you so much. Yes, I didn't see, the script.
Difference between A.
Yeah,
Yeah,
I,
so
I looked at your letters topologically instead of geometrically. My bad.
So so these are with respect to each of the component unital C-star algebras in the respective spectral triples. And we have a notion, so our connecting maps between each of the spectral triples. So we have a notion of isometric morphism between them. So these maps here are connecting maps between the unital C-star algebras. Here are maps between the Hilbert spaces, and they play with the indexing set nicely. And so then the inductive system of spectral triples is this family of spectral triples together with each paired with the corresponding set of maps and respective smooth subalgebras. And that's a way in which one can define an inductive system of spectral triples in the sense of Florcel and Gorbanpour. And
Sorry, yes. Could you explain exactly what is an isometric morphism? Yeah, that's what you want?
Yeah.
Please.
The problem is that these isometry probably are not necessarily unitaries.
Yeah.
Unitary
well,
transformations.
the unitary should be for the big I's, because those are between the Hilbert spaces. But then I would think with the isometric ones, that would mean that they would have to, there's the star operation. So when you have those types of maps between C-star algebras, then that should preserve the distances or the sizes.
Wait a moment. So is this isometry?
If I have to guess, I would say that
an
I
isometry
is the
between
partial
Hilbert
isometry.
spaces?
Okay.
Well, these would be isometries. These ones are isometries between C-star algebras. And then these ones, these big I's,
Are homomorphs.
are between Hilbert spaces.
Yes.
Yes.
Yeah, but there must be some conditions. So there is no compatibility condition between phi and I and T. I mean,
What about commutation with the THERESE?
Oh, so that's on the next, there's something like that on the next slide.
where?
Oh, here.
Yes.
Yes.
So that's in the notion of, so here's just an inductive system of spectral triples, but there's also a sort of subtlety that, so there's a way to define the inductive realization of an inductive system of spectral triples. And so that's where one starts to be more careful about the different domains. So we have the inductive limit of the corresponding unital C-star algebras, the Hilbert space, and we have the connecting maps and the inductive limit of the family of representations. And so making sure that the domains are well behaved, then we can define a Dirac operator on the inductive realization. And
Sorry,
just
but
two
it is
things.
only for the direct limit. Yeah, our question was about the compatibility with respect to this morphism between members of this system.
Exactly, yes. And it's not explained here at all.
Well,
It's
I
not
think
explained.
here so I didn't put all the details, but here this has to do with the way I only put down how the composition plays.
Yeah, but that's the obvious part.
Yeah, yeah.
And
So what is the commutation relation between phi's and i's with these?
because this is crucial to understand. I mean, if you don't understand morphisms, forget the limit. I mean, it's.
Mm.
And we
Also
don't
one
understand
thing-
morphisms. I would like to see a definition of this isometric morphism. I know you have a star homomorphism between sister algebras. Yes, you have the linear map between Hilbert spaces. Yes, obvious. But that's it. The rest, I don't know. And I bet there must
So
be.
you would
and
say,
part-
I think it would have to do with how the representations, how they play with the morphisms too, with the.
Yeah, I would expect it, yes.
Yes.
And also with Diracs, I think that the main objection is about the Dirac operator. So you have
Yes.
your
Yes,
algebra AI, for example, okay? And then this AI is embedded in some larger AJ. And for this AI and also for this AJ, you have two Dirac operators. Somehow this smaller algebra sits in the larger, but it should be compatible with all these Dirac operators. So probably
Yes.
that's the question was about this, yes?
Yes, exactly. Yeah. Compatibility conditions for
Yeah.
this pair of morphisms.
So it's like
Something should be
extension from a
assumed,
smaller
yeah.
to some bigger.
Yeah.
But yeah.
Because you see, morphisms between spectral triples are very important and interesting. So we are not nagging for the sake of nagging. We are,
Oh no, I think I probably left it out I was trying to present it and not necessarily all the details.
But can you write it down right now? I don't know, somehow.
Mm.
With a pen.
You can use the annotate
Yeah.
option.
Yeah, I don't really remember it right now off the top of my head.
Okay, so then let's forget.
But I can send you the paper though.
Mhm.
Florisel Gorban.
Okay.
Yeah. I think it was in transactions. So then this inductive realization might not be a spectral triple. So you could talk about the inductive realization of an inductive system of spectral triples with corresponding smooth subalgebra, and this will happen to be norm dense in the inductive limit C star algebra. So something that they also do is they also so there are different, the inductive limit, the component C star algebra, and the component Dirac operator, it might fail one of the conditions for a spectral triple. It might fail the denseness condition, or it might fail the compact resolvent condition. And those are things that they identify conditions under which this inductive realization is also a spectral triple. And so the examples that they considered, they showed that the AF algebras by Christensen and Vaughan, and also those of Kahn for the commutative C-star algebras of continuous functions on a counter set, that those are all spectral triples that can be written as an inductive realization of a countable inductive system of finite dimensional spectral triples. And while in contrast, our spectral triples for non-commutative solenoids, well, those can be written as an inductive realization of a countable system of spectral triples for rotation algebras. So it's a different class of, examples to add to their inductive systems of finite dimensional spectral triples. And so here's how one might write our spectral triples as an inductive system of spectral triples. And these are each the spectral triples for on the quantum tori. And this can, not only can this the inductive realization of this inductive system of spectral triples, like it can not only can be written as inductive realization, our spectral triple on the non-commutative solenoid also satisfies the conditions that I mentioned earlier that Florissel and Gorbanpour identified, so that the inductive realization is itself also a spectral triple. And it turns out too that our spectral triples, they also happen to induce quantum compact metric space structure in the sense of Riefel. And a quantum compact metric space is a pairing of a unital C-star algebra with a semi-norm, and the semi-norm is defined on a dense subspace of the self-adjoint elements of the unital C-star algebra. It satisfies some kind of Leibniz inequality, and it vanishes on scalar multiples of the identity. And the associated Monge-Konorovich metric on the state space metrizes the weak star topology on the state space. And so when a semi-norm exhibits those properties with respect to unital C-star algebra, then the pairing together defines a quantum compact metric space. And non-commutative geometry via quantum compact metric spaces can be viewed as a kind of non-commutative metric geometry, because every compact metric space we can from every compact metric space define a quantum compact metric space. So for our unital C-star algebra, take C of x, and then for the semi-norm, take the Lipschitz semi-norm with respect to the distance, the metric for the compact metric space. Then this pairing satisfies all the conditions for a quantum compact metric space. So the prototype is the compact metric spaces. And also, to continue further with the analogy with metric geometry, if I take the Gelfand transform, that's an isometry from so we have a copy of the compact metric space lying inside of the state space equipped with the Monge-Konorovich metric. So all of the metric information from the original space can be recovered in this setting. But of course, that maybe there might be more information in the state space. And if we develop tools from non-commutative geometry, then we can, have an enriched framework in which to study commutative spaces. So even in the case of, so here's another commutative setting, even just the commutative setting of the Cantor set, Aguilar and Lopez showed that you could still have metrics that agree on the Dirac measures, but still, differ on a dense set outside of the Dirac measures. And so these are still different quantum compact metric spaces in the commutative setting, even though you can still recover the metric of the original space.
Sorry, I have two problems. One is that you call this map the Gelfand transform. I think that the Gelfand transform is reserved for the mapping between algebras. Yes, you take some possibly non-commutative algebra and you consider the function on the spectrum understood as a set of all multiplicative functionals. So this is only remark, and I have a question: why do you call this map x hat? So x is a variable, so this map should be called probably delta, just delta. Delta takes x in a metric space and sends it to delta of x. Yes.
We have
Which is delta.
Yes.
Yeah. It should,
X hat looks strange. Yes.
Okay.
of course.
This map, it would be better to call this map just delta. Yes.
But where do you see this Gelfand transform? I don't see it here.
It was set. It is not written, but
Well, in terms of evaluation,
Okay.
Gelfand
image-
transform takes an element
The
in
image
your
of
algebra
of delta is the image of this transform. Multiplicative functions.
By the
just
way,
states, yes, just
Yes, delta x is what is denoted the x hat usually, right? delta x is the state.
No.
No, 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 no.
No, x
It's
hat
not
is the
delta.
node for an x lying in an algebra. If you have an algebra, then x hat is a function on
Yeah.
the spectrum, and this is defined as on a linear multiplicative function, let's say omega, in a way that x hat of omega is omega of x. It's just like a canonical embedding into second dual, but
Okay,
this context
yes,
of,
yes.
multiplicative functional is called Gelfand transform. And this is on the level of algebras, not on
Yeah.
the level of space.
Space.
Here we
Yeah,
are
so
on the level of
Delta
space.
is dual to hat.
Yeah.
Yeah,
Delta is dual.
delta is dual.
Yep. Yep.
Exactly. Mhm.
Yep. Yep. So the dual Gelfand transform.
Yeah.
So that's the, so I should call it the dual Gelfand transform.
Okay.
By the way, since we are discussing, I digged out the definition, Teresa. Thank you for pointing it out where it is. And it's actually very simple. So I will not share the screen because I can easily explain it to you. So you have basic preservation and commutation properties. So phi, the star unit of star homomorphism, have to preserve these dense smooth subalgebras. So this is for phi.
Yes.
When it comes to I, there's a bounded map between Hilbert spaces, then it has to preserve domains of Dirac operators.
So it's an intertwiner.
And then you have to have commutation relations. I has to commute with pi, you know, so I pi 1 must be the same as pi 2 I and phi and so on, the obvious combination. And then I and D1 is the same as D2 and I. So completely obvious commutativity and completely natural preservations. For I, it's the domain of the Dirac. For phi, this is a smooth subalgebra. So yes, it's just the definition before the definition you typed up. So yeah. And then you say that this is an isometric if phi is injective and I is isometric between Hilbert spaces. Okay, so now it's clear.
Yeah, it's also
Right.
so
Yeah.
I wasn't mentioning this, but also one should remember that monomorphism between C-star algebras is automatically isometric. So this isometry should mean something more.
Yeah, but this isometry is reserved to this
Yes.
bounded linear map between Hilbert spaces.
Yes. So you explained how it is defined, and this is something more. So
Yep.
it is
I'm
possible.
happy now.
Thank you.
Okay, so here's a non-commutative example of a finite dimensional quantum compact metric space. So taking as the unital C-star algebra, the complex valued n by n matrices that are normal and have only real eigenvalues. And so basically for the semi-norm, take the normalized trace and take this difference. So this is a semi-norm that when you equip this unital C-star algebra with this semi-norm, happens to have the structure of a quantum compact metric space. So our spectral, so if you have a spectral triple, then a natural semi-norm to consider is the commutator with the Dirac operator, the norm of the commutator with the Dirac operator. And it turns out that when you take our spectral triple and equip the non-commutative solenoid with that semi-norm, then you get a quantum compact metric space. And also, when you restrict it appropriately, you also get a quantum compact metric space for each of the quantum tori in the direct limit from which you can realize the non-commutative solenoid. And it turns out that this relies on the condition. So this is where the additional property that the length function be of bounded doubling gets you spectral triples that also induce quantum compact metric space structure. And so those were some of the things that especially Long and Wu worked out in some of their papers for the twisted setting.
So could you remind me, what is this theta to n for a given theta?
This one?
No. You have theta. And then you have sigma theta to n.
Oh, because in the sequence, we only take the even ones.
Okay.
So we only take the
For this-
rotation algebras associated with the even elements in the sequence.
So I forgot why we index these thetas by even numbers and Dirac operators by usual integers. Okay. So,
Right, because it'll still be 1 over p to the n z with that restriction of the length function. So going on to dense smooth subalgebras of non-commutative solenoids. So if you have a unital star subalgebra of a unital Banach algebra, we say that the unital star subalgebra is a spectral invariant star subalgebra if the invertible elements of it are precisely those elements that are also invertible in the larger algebra. And note that so using SI for short, that the unital star subalgebra is SI in the unital Banach algebra, if and only if for every element in the unital star subalgebra, the spectrum in the unital star algebra is the same as the spectrum of it in the larger algebra. And so this is a question that was posed by Long and Wu. So for a fixed prime P and a fixed sequence in omega P, does there exist a dense and spectral invariant star subalgebra of this, so that should have an S there, of this non-commutative solenoid on which this semi-norm is finite. So that's another typo. That should be an S for theta solenoid. So, so that was an additional question posed at the end of one of their papers, considering the domains of these semi-norms, whether you could find a spectral invariant star subalgebra. So, and I mean, this is an analogy within the manifold case. The smooth functions in C of M are dense, but they're also stable under the holomorphic functional calculus. And so this led us to consider unital Fouché star subalgebras, because it turns out, so I think Schweitzer showed that that these are spectral invariant if and only if the algebra is stable under the holomorphic functional calculus. So in our search for an answer to that question, that led us to consider Fouché star subalgebras. And under these hypotheses, the K theory of the unital Fouché star subalgebra will be same as the K theory of the larger unital C star algebra. So it captures the K theory of the C star algebra. And so we decided to also study Fouché star algebras with to incorporate the twisted structure in our Fouché star subalgebras. So more generally, a Fouché algebra, it arises from a twisted group C star algebra. Its topology can be induced by a collection of semi-norms that are each submultiplicative. And that's where the role of the twist comes in with their submultiplicative with respect to the twisted convolution product. And so here we have so here is our candidate. This is what we showed. We proved a lot of theorems to show that this is the sought after spectral invariant star subalgebra of this theta solenoid. So this is a space of complex valued functions on the group, such that for each non-zero, for non-negative S, this function f of 1 plus the length function to the power of S is a twisted L1 function. And here, and so we needed a collection of semi-norms. So these are in fact norms. And so so here's the collection of semi-norms by which we define our by which the topology is induced. So you can see the role of the length function in this. And so something to point out is that our dense smooth subalgebras, they don't have any requirements on the length function to get this spectral invariant property. So unlike our, for the spectral triples and the quantum compact metric spaces, we needed the length functions to have additional properties. But to get the spectral invariance, we only needed that the group be countable, discrete, and nilpotent. Those were the only conditions we needed to be able to leverage results from Schweitzer, Jolisant, G, Alstad, Groschnigen, Lenert, Ludwig, Hilinitsky, and Barnes, among others.
It's Hulanitsky.
Nitsky, sorry, Hulanitsky.
Yeah, I mean he was from my hometown, so.
Oh wow. So in that sense, it's very general. If you just want to be able to, take a length function, so long as the group has these properties, you can take our construction and make a spectral invariant star subalgebra.
I have a question. I would like to understand better this space H1 infinity L. Could we say that it's a kind of fresher version of the Sobolev space, in a sense?
Yeah, it's kind of like a Sobolev space, and the context, and so we adapt. Like, I think that in the papers we looked at, there wasn't quite the twist. And so we just kind of went through some of the proofs to see when we added the twist if the bounds still held, which a lot of them did. But it is a sort of Sobolev type space, and we looked at some papers on like rapid decay type functions.
Please forgive me, but what is this twist again? The sigma is what?
So the sigma is just a 2 cocycle. It's the same 2 cocycle taking values in the unit circle.
Uh-huh.
So it's the same one. And it doesn't show up here, but it shows up when we define the convolution product. So it's a little bit confusing in that sense, that it doesn't show up in this definition, but in proving some different things and getting bounds on products, like submultiplicativity, because we had to look at the submultiplicative part. Then the twist comes.
Sorry, is this space an algebra? H1 infinity L, is it an algebra?
I would say yes. I haven't thought about that.
So if it is, then
It
sigma
is an
plays a
algebra
role.
because it's a dense star
If not,
subalgebra.
then sigma is irrelevant.
Is what?
If this is a subalgebra or algebra, then sigma plays a role because you are using mass convolution. But okay. But if it's only a kind of fresh space, okay, linear space, then sigma is irrelevant.
That's why I was so surprised, because I say H, I think a Hilbert space or something of a sort, and when I see sigma, I'm completely taken aback because it's counterintuitive. Like when you have L1 gamma sigma, again, I was thinking about L1 as some Banach space, right? And why sigma? Well, how does it influence the Banach space?
Right, but when you look at because when you look at the submultiplicativity, though, that's going to play a role.
So it's an algebra.
Yes.
So submultiplicativity means that you are taking this property with respect to this product.
Okay, so then sigma is, yes.
Yeah. Okay.
So then that was the general part. And then let's see, so in order to get up to the level of like the twisted group C-star algebra, well, we first showed that that this is spectral invariant in the twisted L1 functions. So then the next step, which required a lot of steps, a lot of theorems, was to show that this is spectral invariant in the twisted group C-star algebra. And so then we had to be able to view these, we had to be able to leverage results about other group structures. So this twisted group C-star algebra can be viewed as a quotient of a nilpotent group C-star algebra, and in this particular way. So we have a countable discrete abelian group, we have a multiplier. So define this group in this way and define the multiplication like this.
Now we can see sigma, all right?
Yeah. And so if you give this the product topology, this becomes a locally compact second countable group. And if you have a non-trivial sigma and you have an abelian group, then this happens to be a two-step nilpotent group. And you can describe the harm measure explicitly in this way. And when you define the group convolution with respect to this measure, so I think that's what Groschnig and Lerner called those Heisenberg type groups. So if you construct a unitary group representation of H sigma on the L2 functions, then this can be viewed as a quotient of this group algebra. And by the way, this happens to be an amenable one too. Point that out.
So if I understand, sorry, if I understand, this H refers to Heisenberg here.
Heisenberg type, yeah.
Yeah, okay.
And so being able to view our twisted group C-star algebra in this lens, that's what allowed us to be able to get our non-commutative Wiener's lemma. So, this allows us to get the spectral invariance of the L1 functions, of the twisted L1 functions in the L2 functions. And so those were, we needed that in a result from like Ludwig about symmetric groups to get into a particular setting that Ari Alstad worked out to be able to come to this conclusion. And so, and of course, in particulars means that if we have invertibility in this Banach star algebra, if and only if we have invertibility in the larger algebra.
Sorry, is abelianity of, or abelianness of this gamma necessary for this property?
So I think that it might actually be that it might be okay for it to just be nilpotent, and we just kept abelian because ZP cross ZP is abelian. Because all of this was done just so that we could get.
But I'm asking about this equality, this spectrum with respect to L1. Does this equality need gamma to be abelian?
I don't think that gamma needs to be necessarily abelian. It might need to be nilpotent, though.
Okay, thank you.
Yeah. And so we only just highlighted abelian to, you know, to make it a more obvious fit with our original ZP cross ZP.
But I'm quite confused. Abelian and nilpotent are totally different properties. So
no, nilpotent is like close to abelian. So it's the next step.
yeah, but if it's abelian, it's not necessarily nilpotent, right?
But this is two-step nilpotent.
Two-step nilpotent. Oh.
Okay.
The next step after abelian.
Okay. So some nilpotence for commutators, maybe. Okay. Thanks. Mm-hmm.
So and so applying the non-commutative Wiener's lemma, then this gets us a spectral invariance in the finally, not just at the level of the twisted L1 functions, but at the level of the twisted group C-star algebra. And so therefore, in analogy with the classical setting, this is also stable under the holomorphic functional calculus. And so just to give further motivation for why this is a good choice of dense smooth subalgebra. So remember this like sort of key equality. And so so the consequences of this equality for every function in this dense star subalgebra. So if I take such a function and take its semi-norm, then I get this series of inequalities. And okay, so here we have, so that's where we apply this over here. That comes over here. And then, well, that's of course bounded by this, but that's exactly the definition of this norm. And because these functions are in this space, that's going to be finite. And you can, verify by induction that when you have, when you iterate the commutants, then that these are continued to be bounded, then seeing this as a kind of non-commutative form of higher order differentiation, then this is further validation of our choice of this dense star subalgebra as a smooth subalgebra in the twisted group C-star algebra.
Sorry, I'm confused. Why you call it commutants, not commutators?
Commutators, iterated commutators.
Yeah, I don't know why I put that. I should have put commutators.
Okay. Okay.
So now that we have a dense smooth subalgebra that's spectral invariant, then, well, okay, that would be the next step, is to see what other questions we can study about these, about inductive limit C-star algebras as non-commutative manifolds. And so now that we have this result, we can take our original result about spectral triples and specify this choice of smooth star subalgebra, dense star subalgebra. And we can, furthermore, not just say that such a one exists, but also that it's stable under the holomorphic functional calculus. And so then maybe another question to ask would be, well, we have our inductive system of C-star algebras corresponding to the inductive system of spectral triples. So we could also consider the inductive system of twisted Fréchet star subalgebras. These are each star isomorphic. So these each capture the K theory, right, of each of these inductive tori. And they're also stable in the holomorphic functional calculus. So then it would be interesting to ask, what insights could you get about the non-commutative geometry of the non-commutative non-commutative solenoid in the inductive limit by studying each of these respective K theories? And that's it. And thank you.
Okay, thank you so much. Let's
I
continue.
try hard to talk slower.
Let's continue with questions. Who wants to begin? Adam?
I think that I need some time to formulate my question. So right now I don't want to bother.
I would have a question.
Go ahead.
If I could. In the very last moment of your talk, you suggested that we can think about this solenoid as a kind of smooth manifold, non-commutative smooth manifold in a sense.
Yes.
But classical solenoids are very far from being manifolds. Okay, it's a very, very strange space geometrically from the point of view of the classical geometry. Okay, so what is the lesson from this point of view? That allowing non-commutative smooth spaces, we can speak about spaces which are very far from being smooth in a classical sense. Is it
Yes.
a good message? Okay, okay.
Or to me, starting off from fractals, that is a still motivation for developing tools for non-commutative geometry, is to be able to define and study geometry for spaces that are not well behaved in a classical for classical tools.
Francesco? I see you raise your hand. Francesco?
Yes. Okay, thanks. Now I have a question, but it's actually about inductive limits of spectral triples. So I don't know if it is appropriate, but I was curious, at least in the AF case, in the case of AF algebras, if you have a description, for example, of Dirac operator in terms of Brattelli diagrams or some kind of diagram or a groupoid picture.
Well, I haven't looked at Brattelli diagrams in this context, and I haven't studied groupoids ever.
Okay. I mean, maybe there is no relation at all. It's just that since instead of thinking of them as limits, maybe there is a description in terms of some kind of graph. Okay, but it was just a comment or question unrelated, probably. Thanks.
But that would be certainly interesting to see what kind of, how maybe some structure in the graph gets encoded in structure in the inductive system.
Adam, you seem ready to jump with a question. Yes, go ahead, Adam.
Yes. Maybe it's more like a remark, not a question, and it is also related to what Thomas was saying. So I think the problem is with this notion of commutative spectral triple. So commutative spectral triple is a spectral triple for which the underlying algebra is commutative, but in order to be able to reconstruct the manifold, you need a bunch of conditions, non-trivial conditions, very many of them. So you are able to get commutative as being the algebra being commutative, spectral triples coming from, for example, from some fractals and so on. So I believe that maybe the story with this solenoid is in this period. You remember, you in the definition of spectral triple, you were asking about this order one condition. It was not present, so it is not really like a manifold. So I think that the slogan that spectral triple is like a non-commutative manifold, no, is much more general.
Yes.
And in order to get something which is really like a Riemannian or spin manifold, you need a bunch of other conditions, smoothness, and also this projectivity of modules and so on. So, or the one condition, this Hochschild cocycle condition for volume form, and so on and so on.
Yeah.
So the name manifold is very demanding, as you said.
Yes.
But in the classical context, there are spaces which are very closely related to manifolds, not being manifolds, like differential spaces of Sikorski, for instance. I'm not so sure if classical solenoids are differential spaces, but they are very close to such spaces which are more exotic than manifolds, but still in the spirit of smooth structure.
That's interesting.
Yeah. So of course there is no fundamental cycle. There is no the question of orientability, maybe, but in a sense there are singular spaces very close related to classical spaces.
Yes, I agree, but some of these conditions should be maybe somehow reformulated on the level of spectral triples.
Of course.
Should be there. Yeah, yes, there should be there something, at least.
So definitely there are some kind of smooth spaces. Not saying that they are manifolds,
Yeah.
but they are smooth spaces in the sense of Sikorski, for instance,
Mhm,
or in this period at least.
mhm, mhm.
Yeah.
Yeah, this is a very good point.
Are also examples, yes.
So therefore, I asked at the beginning, are classical solenoids somehow related to this construction?
Mhm.
Yeah, for some sequences of theta, maybe there is some, at least, I don't know, maybe at least some Morita equivalence
Mm.
with the classical solenoids. I don't know.
And maybe also one
mean-
should remember that. Okay, sorry, go on.
I mean, that's something that I've thought to study, because this construction should also apply to commutative solenoids. And so then the commutative solenoid, there is like, target types of geometric quantities to recover.
Yeah.
And also one should remember that at least on the level of the sister algebras, if you are considering inductive limits of commutative sister algebras, this corresponds to projective limits of the underlying spaces, and
Yeah, but
manifolds. Yes, so the manifold structure. Yeah, so the manifold structure need not to survive in this process. I don't see a reason why.
Yeah, but in this direction, it's not so bad. It's like, for instance, if you are constructing classifying spaces of classical groups, for instance, you can speak about infinite
Joins.
complex projective spaces or Grassmannians or flag spaces. Okay,
Mhm.
so they are. But the problem here is that this condition of compatibility with Dirac operator is something like choosing some connections. So let me explain. If you have an injective star homomorphism between star algebras, okay, so this is like a vibration, dually speaking.
Yeah.
If you want to extend the Dirac operator, which should be meant as a kind of differential operator, from the smaller algebra to the bigger algebra, it's like taking it's like lifting of derivations from the base to the total space of this vibration.
Yes, that's a connection.
So this is like a choice of the connection. So in this language, this limiting algebra, after this condition of commuting with Dirac of these phi's and i's, okay, it's like a system of connections on these extensions, okay. So this makes this space from the classical point of view very complicated, because classically the choice of a connection is an arbitrary part of this smooth structure. Of course, topologically, it doesn't change a lot. So probably K theory can be computed using different, or some characteristic classes could be computed using different connections. Okay, but for this smooth structure, this arbitrary choice of this lifting of derivations or this extension of the Dirac, okay, this makes this construction very special at the end of the day. It's an infinite system of choices. Yeah. So maybe we shouldn't think about these spaces as being strict analogs of solenoids. Maybe they are somehow equivalent, topological equivalent, or Morita equivalent to some solenoids, but not from the point of view of metric geometry. So still, I do not understand the relation between classical solenoids and these non-commutative ones. So I would like to understand it better.
Wait, so if you take her definitions in the commutative setting.
So it's not clear to me under which choice of these thetas, the sequence of thetas, you obtain a commutative algebra.
Yeah, that's a good point, yes.
Because this cos cycle already makes everything non-commutative for its own sake, regardless.
Yeah, that's a good question. Teresa, can you say under which conditions your C-star algebra of a non-commutative solenoid is actually commutative?
Right. I haven't thought about that, but I think off the top of my head, I would either say a sequence of zeros or maybe just, I don't want constants, but definitely zeros.
Yeah, but the question was probably about non-trivial.
But that is something that I have thought is a next step for me to study, is to see how this plays out in the commutative setting, because it does apply to the commutative setting.
All right, I think it's time to wind it up. Any more questions from the room? Nope. Any more questions from the Zoom? Nope. Okay, so let us thank Teresa again. So much.
Thank you very much, and for all your, very generous comments. And
I hope you enjoyed it.
yes, definitely.
Good. Okay, I have a comment from Chile. Very interesting. So you see, our choice of timing is not so silly because 4 people are from Americas. So let me stop recording now.